Committee of National Conference on Advances in Computing Technology 2020. We have gathered here for the post-conference talk of the conference. I extend a warm welcome to all the dignitaries and all the participants and all others who have joined in this meeting. We'll start the session with a talk on Ramanujan in computing. The talk is being arranged as a tribute to the legendary Indian mathematician Srinivasa Ramanujan. This year happens to be the centenary year of his death. On behalf of the organizing committee, I would like to invite Mr. Sajay K.R., Associate Professor of MCA Department, Vidya Academy of Science and Technology, to introduce the speaker of the post-conference talk, Dr. V N Krishnachandran. Sir, please.
Thank you, ma'am. A very good morning to one and all. I feel highly privileged to introduce Dr. V N Krishnachandran, who is now going to make the first post-conference talk this morning. This talk is about Ramanujan in computing, and we are all waiting to listen to the talk. Dr. Krishnachandran is currently the head of the MCA Department of Vidya. Before joining Vidya, he was teaching mathematics in Government Engineering College, Thrissur for a long time. He retired from government service as principal of Government Victoria College, Palakkad. He has spent a year in Loughborough University of Technology, UK as a British Council scholar. His area of specialization and research is theory of semigroups with focus on the topology of the semigroup of linear endomorphisms. He has published several research papers in international journals. Recently, he published an e-book on machine learning, which has become the standard textbook in machine learning for BTech students of APJ Abdul Kalam Technological University. Has considerable expertise in the tech typesetting system created by DNet and its many later variants like Latin. He is ardent popularizer of computer algebra systems like Maple and Mathematica. The NC department of the college organized an AICT-sponsored 2-week faculty development program on computer algebra systems in January 2020. He is an early entrant to the world of computer programming and is deeply interested in the art and craft of problem solving using computers. He loves contributing to Wikipedia, the web-based free encyclopedia that anyone can edit, enriching its content by contributing articles, editing existing pages, and uploading image files. On behalf of the organizing committee, I humbly request you to make the presentation. Sir, please, over to you, sir.
Thank you for that fine introduction about me. As has been announced, this is a post-conference talk to the National Conference on Advances in Computing Technology being organized by the Department of Computer Applications of Vidya Academy of Science and Technology. The conference concluded yesterday evening. We have one more talk today after my presentation. The talk is being arranged as a tribute to the legendary mathematician, Indian mathematician, Srinivasa Ramanujan. He died in April 1920, and this year is the centenary year of his death. It is appropriate that we pay tributes to him by talking about his ideas that have influenced advances in computing technology. So in that sense, the topic is also highly relevant to the topic of the two-day conference. The Ramanujan was a prolific contributor to mathematics. His area of specialization, if one can say that, was number theory, and he has made tremendous, unimaginable amount of contribution to that area. But he died in 1920, and in the subsequent years, the world got transformed, and studying number theory became unfashionable among mathematicians. There are fashions in science. So after his death, number theory was not a fashionable subject to talk about. Yes. Other subjects, more abstract, came to the fore, and so mathematicians did not give much attention to the work of Srinivasa Ramanujan. However, the situation changed in 1980s, when the world was celebrating the centenary year of his centenary period of his birth. There was a great revival of interest in Ramanujan, and that helped people to have a relook at his work. And this relook generated many developments. And what I am talking about is some of these developments. So with these introductory words, I will move over to the presentation. I will talk to you with the help of the presentation. Okay, so let me please move over to the presentation. Okay, so the topic is Ramanujan computing, and it is organized as a post-conference talk as part of the National Conference on Computing Technologies 2020. Conference is organized jointly with Computer Society of India and Indian Society of Technical Education. So this talk is, as I already mentioned, a tribute to Srinivasa Ramanujan in the centenary year of his death. Okay, this is a famous photograph of Srinivasa Ramanujan. He was born on 22nd December 1887, died 26th April 1920. And during this talk, I'll be talking about these three ideas. Ramanujan series in pi computations. Then I'll talk about what are now called Ramanujan machines. And then about Ramanujan graphs. The last two topics, Ramanujan machines and Ramanujan graphs, Ramanujan is only present in the background, not directly derived from his work, but his ideas just stand behind those concepts. Okay, I'll explain. Let me just quickly go through some of the very important points in his life. Just a recall. He was born 22nd December 1887. He passed the matriculation examination, that is our current 10th standard, in 1903. Joined Pachaya Chiapas College in Madras in 1905, but he did not complete the studies. He did not even pass the +2 examination because he was only interested in mathematics. He passed in mathematics, but failed in most of the other subjects. Even in mathematics, strangely, even in mathematics, he did not get a 100% marks. He had only 70% marks because he was interested only in one area of mathematics, algebra and number theory. So he did not even care to answer questions in geometry. Probably that is the reason why he did not secure a 100% mark in mathematics. Strange, but that is true. He published his first paper in 1911 and left for England in 1914. So the related stories are all well known. He writing a letter to G.H. Hardy and the English mathematicians making an earnest effort to bring Ramanujan to Cambridge. All these are very, very well known, very moving stories. So since we have no time to explain those things, I just go over that. I request all of you to have a look at the story of Ramanujan. It's very inspiring. Of course, he got a BA degree in Cambridge for research and became a fellow of Royal Society in 1980, returned to India in 1990, and died on 26 April 1920. These are some of the brief milestones in the life of Ramanujan. Now, regarding the mathematics of Ramanujan, okay, the mathematics of Ramanujan is contained in 3 notebooks written in his own hand. And these notebooks were written before his departure to England. The first notebook, a page of which is shown here, is in his own hand. 100-year-old pages, so pages look yellow and not very readable. Is about 300 plus pages. Second notebook also has a similar number of pages. Last notebook is notebook 3, has only a 26 or 25 pages, a small one. So these notebooks contain the results that were discovered by Ramanujan before his departure to England. Whatever he discovered while he was in England were published in research papers. And then all these papers have been collected and published as a single volume by the Cambridge University Press in 1927. Now, there is also a lost notebook. That title has a double inaccuracy, double error. It is not lost, and it is not a notebook, but people refer to it as a lost notebook. It contains a loose sheet of pages, and it is not lost, it is now available. It is called a lost notebook because people knew of its existence, but they could not trace that. So it was just believed that it was lost one time. So at the time it was referred to as a lost notebook, it was really lost. But now it has surfaced and it contains a lot of research. Now, an English professor has published 5 volumes of books, 5 volumes, each about 250 plus pages, describing the entire mathematics in the lost notebook alone. All the mathematics that is contained in the lost notebook, it is a bundle of pages, been explained in detail, and that explanation took around 5 volumes, each containing 250 pages. So you can think of the depth of mathematics contained in these volumes. Yeah, they have estimated that Ramanujan compiled nearly 3,900 results Each of them can be called a theorem, mostly in the form of identities and equations. 3,900 results in a short life of about 30-33 years. Okay, of course, a few of them are known to be false, only very few, and some of them are already known before he discovered them. Most of his claims are really original and unique, and they have been proved correct later. Ramanujan did not give proofs of most of these results. It is said that he used to do the computations and calculations in a slate because paper was not affordable to him then. So he cannot afford the luxury of using a pen and a paper to do the computations. He used a slate, and whenever he get a result, the result will be copied on the paper, and the derivations and all others were erased, and so that they are not now available. So the mathematicians have the task of rediscovering the way in which Ramanujan arrived at these results. So that is why he took this mathematician professor 5 volumes to explain the mathematics behind the contents of the lost notebook. Okay, so this is only just an introduction. So we'll be seeing some of the results that Ramanujan has found and their applications in computing technologies. We will see at least 2 or 3 such results. Okay, so one area where Ramanujan's work has a direct implication is in the computation of the values of pi. Computation of the digits of pi. All of you know what pi is. It is the ratio of the circumference of a circle to its diameter. It's a very, very mysterious number. Its value has never been known accurately. It is an irrational number. More than that, it is what is called a transcendental number. It is not the equation of a polynomial. It's a very mysterious number. And people have tried to get the value of pi the most accurately as possible. So it is a passion among some people to calculate the value of pi to as many digits as possible. So in this quest, a formula of Ramanujan happened to be very crucial. It is the story that I am going to say now. Okay, so before that, let us see some of the earlier historical values of pi, history of pi computations. See the Rhine papyrus, that is some document obtained from the Egyptian civilization around 1650 BCE, before the Common Era, that contains a problem from which we can indirectly guess that the value of pi they have used is approximately this. Pi equals 4 into 8 by 9 whole square comes to roughly 3.160. So the Rhine papyrus has a reference to a problem which contains this value. Then the Shilpa Sutras, see, they are the works, mathematical works from ancient India, 800 to 200 BCE. The Shilpa Sutras are actually manuals for the construction of Vedic altars. So that contains a reference. There are actually 8 different values have been specified in those Shilpa Sutras. The one which is closest to the actual value of pi is what is displayed here. Pi is equal to 3.088. Now, I'm giving a reference to a Chinese mathematical book I'm trying to give examples from different civilizations. The Egyptian civilization, the Indian civilization, the Chinese civilization. The Chinese civilization, there is a mathematical book written, the dates are not exactly known, during the period of the Zhou dynasty that extended from 1046 to 246 BCE. The book was compiled and completed sometime during that period. In that book, there is a value which is given as pi equal to 3. So these are the ancient beginnings. Now we are going to talk about the value of pi correct to the end. We will see the value of pi is now known to correct to 50 trillion digits. That is where we stand now from these ancient beginnings. Okay, so now there are several algorithms. Perhaps the first algorithm was developed by Archimedes. Very interesting. See, he constructed regular polygons having the same length, sides, and same angles. Regular polygons inscribed and circumscribed in a circle, and then computed the perimeters of the inscribed polygon and of the circumscribed polygon. So the value of pi must lie between these two. He gradually increased the number of sides of the polygons, and he had a method. Archimedes started with a hexagon, and then he doubled the number of sides, considered a polygon with the 12 sides, then a polygon with the 24 sides, and then a polygon with the 48 sides, and finally a polygon with the 96 sides. Regular polygon, 96 sides, inscribed and circumscribed, and calculated the perimeters, and using that, he arrived at these limits: 223 by 71 less than by pi less than 22 by 7. That 22 by 7 is the commonly accepted value nowadays. Perhaps the origin of that formula, that value, can be traced to Archimedes. Okay, see, this method has been in use for quite some time. The maximum value that is obtained was correct to 39 digits in 1630, but that method was abandoned, and later infinite series were used, and it began to obtain better accurate values. So I'm mentioning infinite series, and that leads us to this legendary mathematician. Okay, you must have seen this. He is Sangamagrama Madhava, a great mathematician who survived in Kerala. So this is an image of Sangamagrama Madhava. I see there was no photographs then. He lived around 1340, 1425. No photographs were available. So this was an image constructed by a voluntary organization based in Kochi. It is called Madhava Ganitha Kendra. They interviewed the descendants of Sangamagrama Madhava and the earliest photographs of the descendants. And from that, using computer morphing and other things, they constructed this image of Sangamagrama. So now it is, if you Google, you will get this picture. So before I say that, see, Sangamagrama is said to have lived in Irinyalakuda, our own Irinyalakuda in Thrissur. And there is a family called Irinyadapalli, and he said to have lived there. So the people from Madhava Ganitha Kendra studied the features of the descendants and constructed this image. So Sangamagrama Madhava was from Kerala. He discovered fundamental results in mathematics. The sine series expansions for sin x and cos x were discovered by him for the first time in the world with proof. So here, it's not the time to explain all those things. Okay, I just mentioned the significance of Sangamagrama Madhava in the journey of computation of pi. he calculated the value of pi correct to 11 decimal places, probably using the formula, the result given on the screen. This is a result which is discovered by Madhava. We don't know exactly how he calculated the value. Probably if we choose, take 21 terms in this series and do the calculation, we will get the value obtained by him correct to 11 decimal places. Okay. Then in the long story, there is a very strange person, William Shank, an English mathematician, who spent over 20 years of his life calculating the values of pi. He calculated 707 decimal places by hand. Calculated by hand using some series. Spent 20 years and obtained a value correct was 707 places, but later it was proved that only the 527 places was correct. So the rest of the values were worthless. So this was accomplished in 1893, and this was the longest expansion of pi until the advent of electronic digital computers. Okay, now enter Ramanujan. How? Okay. See, look at this. Look at the slide. At the top, I have reproduced a part of the paper which contains a formula which has been used for the computation of pi. It's part of a paper published by Ramanujan in 1914. See only a bottom part of the paper. There is no space in the slide to include all the page. So you can see the two equations 43 and 44. And above that, there is a long list of such expressions, all containing various infinite series for the computation of pi. So this is the equation 44 shown here is only the last one among a long list of such formulas. So remember this formula, this was discovered by Ramanujan and was published in 1914. So somebody used that formula to compute the value of pi. Here, in the paper itself, Ramanujan has made a reference. The last series, 44, is extremely rapidly convergent. That is what Ramanujan was writing. The last series, 44, is extremely rapidly converging. And so taking this cube, okay, this is the full expansion for your benefit. Same thing written in using the sigma notation, that's all. In November 1985, one computer enthusiast, Gosper, employed this series to calculate how many 17 million 526,100 digits of pi in 1925. Using the series that I have shown you. So that is, the Ramanujan series was resurrected and applied to calculate values of pi to so many digits. But there was a problem. See, it was not proved that the series was correct. Nobody has proved. Ramanujan has only stated that the series, no proof was given. So it was only in the form of a conjecture. But later, it was proved only in 1987. Borby was the name of the man who proved this in 1987. So it was proved after the computation. Okay. So now you can see Ramanujan continuously is influencing the subsequent computations. Again, another interesting fact. Now enter Chudnovsky brothers. They are two strange persons. They are two brothers living together. One of them is some physically disabled. The other person is healthy. So the healthy brother is always with the unhealthy brother so that they can help each other. They have built a supercomputer in their home and they developed the algorithms, they developed the mathematics, and they created their own formulas for computation of pi. They obtained the proof of Ramanujan and developed that to create another more fantastic formula. Okay, it's hard. It is even hard to read using ideas on which the Ramanujan series was proved. The two brothers developed another series for 1 by pi. Now this is the standard formula for piling up digits of pi. Remember, Ramanujan is sitting behind this formula. The motivation for arriving at this formula is the Ramanujan series. So whenever we look at this series, we have to feel Ramanujan is sitting behind. So this formula is now used even to compute 2 more digits of pi. Okay? Look at the figure. The above formula, Chudnovsky formula, the Ramanujan sitting behind, has been used the world to create world records in calculations of pi. 2.7 trillion digits, trillion, in December 2009. Now, the latest figure is 50 trillion digits of pi on 29th January 2020, the recent. And that was accomplished using Chudnovsky formula, which was discovered based on Ramanujan's formula. That is how Ramanujan comes in this computing of the values of pi. Okay, so some of you may be thinking, why spend time calculating the values of pi? What is the use of 50 trillion digits of pi? Okay, there are several reasons. One trivial reason is that gives them a lot of pleasure doing that, a lot of attention. The people who do that become great, but that is not the real reason. The real reason, reasons are two: to know whether there is any patterns in the digits, any patterns, any hidden patterns are there in the digits of pi. That is one reason. Another more important reason is to test the trustworthiness of supercomputers. When we make a computer do computations of this scale, will they fail? Will they fail? That has to be tested. So such a huge amount of computation can help us understand whether a computer system, a hardware system, a supercomputer will fail or not. So the value of pi is calculated in two different ways. One way, 50 trillion digits, another way, 50 trillion digits, and the two are compared. So when there are no differences, that gives the world confidence in the computer system in which we are using. Otherwise, how do we know that no error is happening? We cannot do such calculations by hand. What is the guarantee that the computer system is not making any errors? Instead of zeros, is inadvertently putting a 1. How do we know that? We can know that only we put the system to tasks like this. So that is one of the main and important reason for computing the values of pi. So 50 trillion digits is the latest record accomplished in 29 January 2020. It will be broken. So, I expect that it will be broken in the near future. Okay, so that is the influence of Ramanujan. Now here also, I think I will just say one more. It's not only that the Chudnovsky formula is used for the computation of pi in the computer algebra system, Wolfram Mathematica. Mathematica is a computer algebra system. It can produce a large number of any number of digits of pi, and that is accomplished as an application of, accomplished using the Chudnovsky series. So that series, Chudnovsky series, which is based on Ramanujan series, is not something which is a curiosity. It is being actually applied. Wolfram Mathematica is being applied, is being used by mathematicians, engineers, and all others world over routinely. And they use pi routinely. So that formula is being used in that particular software. So I think with that I will close that topic and move over to Ramanujan machines. And this idea is very interesting. Ramanujan machine is not a machine. And Ramanujan machine has actually no connection with Ramanujan. It is a name that is given to some system, computer systems, hardware, logic, programming, etc. The thinking was like this. As I told you at the beginning, Ramanujan wrote down 3,900 plus results. Most of them are identities, equations, and things like that. He simply sit down, take a piece of paper and a pen and write down an identity, as if from nowhere. As if it comes to his mind spontaneously. That is what has been told. So he said that there is one goddess in Namakkal, and that goddess used to give blessings this night and just to inspire him to write this thing. That's a story. It's only a story, as if it happens like that. And so it is as if he is like what many people have called a conjecture machine, a machine which guesses results, which guesses conjectures. A conjecture means something which is a guess, most probably true. It is called a conjecture. So Ramanujan has been compared to or thought of. It's not very funny to hear, but has been thought of as something like a conjecture machine. Some people have referred to him like that. So some people thought, so can we have a machine? Can we have a system, computer system or software system, which produces conjectures? If there is such a system which produces conjectures, the most appropriate name for that system is Ramanujan machines. And that is how the name Ramanujan machine has come about. So it is not an actual machine, a system of computer programs which produces conjectures. Okay, so let's go to the next few slides. I have already explained this. Why the name? Ramanujan has several results in the form of conjectures. Most of these conjectures have been proved true by later mathematicians. Because of this, Ramanujan has been called the conjecture machine. So a machine, whether actual or conceptual, that produces conjectures has been christened as the Ramanujan machine. Okay, the Ramanujan machine, as I mentioned, is not actually a machine. It's only a concept. It exists as a network of computers running algorithms. So presently, what these algorithms do is to produce infinite continued fraction expansions of certain functions, certain constants like e, pi, log 2, etc. So the creators of the machine claim the algorithms have already generated several such expansions. Okay, so I just go through a few slides because that requires an explanation of what is meant to be a continued fraction. And then I will show you some of the results that have been produced by the Ramanujan machine. only a few are shown. You can see plenty of such conjectures by referring to the website of Ramanujan machine. So an expression like this is called a continued fraction. A0 plus A1 by B1 plus then A2 by, like that. So it is called a continued fraction, and it is often expressed in the form that plus is written below along with the denominators. Usually we write plus and usually along with that dividing line. So this notation means that it's a continued fraction. Expressions like this are called continued fractions, and there are continued fractions for pi. This is a continued fraction expansion for pi. The denominators have no pattern. 7, 15, 1, 292, etc. And those numbers have no pattern. Whether these numbers have a pattern, that is one of the interesting things that are being investigated. Now, for the mathematical constant e, we have another continued fraction, but here there is a pattern. You can see the pattern 211, 411, 611, 811, like this. Okay, these are examples for continued fractions. Now, I'll give some examples. I'll just give you one or two examples because there is no meaning in giving any more examples. You can refer to the website if you're interested to know more, to see more such examples. Yeah. Yeah. Look at this. The first one, a series for continued fraction for 4 by 3 pi minus 8 equal to this. This was discovered by the program. This was conjectured by the machine, and it has been proved through later. Second one, E, an expression, a continued fraction for E. This was discovered by the machine, discovered by the program, and then it is proved to be true. So these are conjectures created by the Ramanujan machine. It is a concept, it's a set of programs, it is an algorithm. All these have been proved true. Then there is an example which has not yet been proven. It is a series for log 2. 1 by 1 minus log 2 is expressed as a continued fraction with some expressions. Okay, this has not been yet proven true. So if you refer to this website, if you're interested, you can get more such results. www.ramanujanmachine.com. You can see more details about this machine in that website. Okay. And finally, I will spend a few minutes explaining what are Ramanujan graphs. I thought of talking about this Ramanujan graph at the end because this is a little more mathematical. Okay. See, the story begins with what is known as Ramanujan's tau function, TAU, tau function. The tau function is defined as shown in the slide. And you may wonder what is the use of that. Okay, Ramanujan has studied this and obtained several properties of this. Q into that pi product 1 minus q raised to n whole raised to 24. You may wonder why 24 and things like that. Okay, that is not cannot be easily explained. There are reasons. And when you expand this as a polynomial or an infinite series, tau n is the coefficient of q raised to n. That is the value of tau n. That's a very interesting properties. Ramanujan obtained these values for q tau n. Remember, these are the p is a prime. Tau n, when n is a prime number, calculated 30 values of this. And from these values, okay, it's not necessary to go through all the values. What is interesting is, from these 30 values, Ramanujan derived this result. He conjectured, not proved. He said, probably it is true like this. That is what he's mentioned in his paper. Mod tau of p is less than or equal to 2 raised to 2 into multiplied by p raised to 11 by 2. This he said, probably, and there are reasons to believe, this is exactly the words used by him. Probably, and then he said, there are reasons to believe so, that this is true. It's only a conjecture. And this is known as Ramanujan conjecture. And remember, I told you all others forgot about all these things. And this was proved only much later when there was a revival interest in Ramanujan mathematics. It was proved only in 1974. And this result is crucial. This result is crucial in the definition of Ramanujan graph. Okay. So I'll try to give a brief description of what a Ramanujan graph is. Let's see, to explain that, we require some familiarity with the graph theory and also some familiarity with what is known as spectral graph theory. So since we do not have the time to explain all those things, I skip the details of all those things and give a very broad definition of the concept of a Ramanujan graph as given here. A Ramanujan graph is a graph in graph theory having a very special property, which may call temporarily as the R property. It is not a standard usage. I call it R property. Okay. The members of an important class of graphs, they are called Lubotsky-Phillips-Sarnak graphs, LPS graphs, and denoted by X raised to P, Q. Members of this class of graphs were shown to have the R property. LPS graphs have this R property. In proving that, this has the LPS. LPS graphs have this property. They have used the Ramanujan conjecture, which I have shown in the previous slide. This property. Tau p less than or equal to 2 into p raised to 11 by 2. This property was used in proving that these LPS graphs have this particular property. And so they began to call a graph having this R property as the Ramanujan graph. So this is a slightly indirect way of naming the graph. And so the name has caught on. And now people refer to any graph having this property as the Ramanujan graph. So this is the connection of Ramanujan graph and Ramanujan. So Ramanujan again is influencing the computing technology. Okay, it is not a mere theoretical concept. It has plenty of applications. So even without saying what they are, you can appreciate the significance of the Ramanujan graphs when you look at the applications. Okay, this has applications in network theory. For example, consider the construction of a new telephone network with a high connectivity. We need connectivity with as few edges as possible to minimize the cost. Now, Ramanujan graphs have been used in the design of such networks. That theory is used in studying and designing networks with minimum cost. That is one application of Ramanujan graph. The other applications are again in computer science. We are talking about applications Ramanujan in computing. So the next two applications, Ramanujan graphs has been used for the construction of pseudo-random number generators. A pseudo-random number is a number which has properties of random numbers. They are generated by algorithms. Set of numbers generated by the algorithms are called pseudo-random numbers. They are not actually random. They are produced by certain algorithms. So there are several well-known algorithms for the generation of pseudo-random numbers. The Ramanujan graph has been used for generate as pseudo-random number generators. Okay, so the details again is beyond that. It cannot be explained in a few words. And lastly, yeah, we know what is a hash function, cryptographic hash function. It's a one-way function and has several interesting properties. We cannot find the pre-image resistant, collision resistant, and many properties are there for a cryptographic hash function. And there are several algorithms for cryptographic hash function. And the Ramanujan graphs can also be used in constructing secure cryptographic hash functions. Now, the significance of this observation is that, see, there are reports about quantum cryptography, quantum computations circulating, quantum computations. So there is a fear that the development of quantum computation may break many of the cryptographic systems that you are now using. The development in quantum computation may break the security system that we are now using. And so cryptographic specialists, cryptographers and other specialists are looking for algorithms which are quantum computer resistant. They are called the post-quantum cryptography. And the cryptographic hash functions based on Ramanujan graphs are considered as a possible candidate for generating hash functions in the post-quantum computing world. So that is the significance of the Ramanujan graph in the construction of hash functions. They are considered as a candidate. Possibly, this may be used in a post-quantum world. Post-quantum world means after the development of quantum computation, quantum computing, we can have systems which cannot be broken using the methods of quantum computing. Okay, to give an understanding of the complexity of such graphs, here is an image of a graph which could be used for creating a hash function. So complicated, the nodes are not usual nodes. Each node represents what is called an elliptic curve. Each node is an elliptic curve. So there is a connection between two nodes when they will have a node. So the things are so complicated, not easy to explain. But anyhow, the picture itself gives us the complexity of the graph. Okay, I have overstayed my time. So these are some of the things that I wanted to share with you. If anybody is interested in knowing more about these things, I can give references, I can give books and any other material. So with these words, I conclude my talk. Thank you so much. Thank you. Thank you so much.
Thank you, sir. Thank you. If any queries you have, please raise. Open for discussion. Participants have any questions, please raise the questions. Or you can type in the chat box. I think, sir, no more queries, sir.
Okay, thank you. Thank you so much.
Thank you, sir. Thank you for giving a wonderful talk on Ramanujan, computing on Ramanujan topic. And I would like to thank on behalf of the organizing committee and on behalf of all the participants present here. I deeply appreciate the presentation you made at this post-talk conference. Thank you for being with us today, sir. Thank you very much. Thank you all.